Welcome to a new episode of Dantec Dynamics webinar series on the subject of constant temperature anemometry. My name is Gökhan Ergin and I'm a senior product manager at Dantec, responsible for CTA and microfluidics product lines. My main activities in this role are sensor development and scientific collaborations. Today I will give an introductory lecture on constant temperature anemometry, abbreviated as CTA, also known as Hotwire anemometry or thermal anemometry. During the presentation, I may use any of these terms meaning the technique constant temperature anemometry. The purpose of this presentation is to provide a basic theoretical introduction to the CTA technique used in flow investigations. The seminar is intended for students who are about to begin a measurement campaign using CTA, researchers or decision makers who are considering the CTA technique for their next measurement campaign, or professors and educators who are looking for a brief introductory material to the CTA technique for their subsequent more advanced teaching activities. In practice, the Hotwire anemometry is often used in airflows and in particular for boundary layer studies and during turbulence investigations. We will start by introducing a state-of-the-art thermal anemometry system components, continue with the operating principle, velocity response, error sources, and directional response. We will conclude by providing an application example from a boundary layer investigation. Today, a state-of-the-art CTA measurement system consists of computer-controlled mainframe, velocity and temperature modules, automatic velocity calibrator, and often a directional calibrator, a number of Hotwire probes, system computer, an A to D converter, and of course CTA software for data acquisition and processing. Also, often a traversing system accompanies the CTA system, as Hotwire anemometry is a point measurement technique. The Streamline Pro anemometry system manufactured by Dantec Dynamics is regarded as the state-of-the-art, as it contains all these features in one package. The Streamline Pro mainframe features high-quality electronic components and modern USB LAN connections, various high-precision internal converters, and sub-circuits for square wave test. Each velocity module is plug and play and features a programmable signal conditioner and multiple Wheatstone bridge configurations. These can adapt to various demanding applications. The complicated velocity and directional calibrations of Hotwire probes are turned into a routine task using the Streamline Pro automatic calibrator and the automatic directional calibrator, which is this black part here. Hardware setup, calibrations, data acquisition, and post-processing are performed on the Streamware Pro software. The system computer should have enough storage space for the experiments and should have also sufficient number of connection and expansion ports. The most crucial part of the CTA system is actually the probe, which is selected based on the application. There are some general important considerations in the sensor design of Hotwire probes. First of all, the sensor should have small thermal inertia for good frequency response. Second, the sensor should be short for good spatial resolution, but on the contrary, it needs to be long in order to minimize and loss effects due to conduction. So there's a trade-off between spatial resolution and sensitivity. For high sensitivity, high signal to noise ratio, and high frequency response, a high temperature coefficient of resistance, which is alpha 0, is required. Of course, the sensor should also resist oxidation at high temperatures, where we can get high sensitivity and high signal to noise ratio. The most commonly used Hotwire sensors are thin wires, which have a diameter around 1 micrometers to 5 micrometers. The miniature wire probes have 5 micron diameter and 1.2 millimeter long platinum-plated tungsten wires. These probes are less costly compared to those with gold-plated sensors, which are about 3 millimeters in length, but have gold at the sensor ends. This ensures an accurate 1.25 millimeter long active sensor length, which have several advantages. First of all, reduced heat conduction to the prongs. Second, more uniform temperature distribution along the wire. And finally, reduced prong interference on the measurement. As Hotwire sensors are very fragile, they cannot be used in some environments where more rugged sensors are required. In such cases, hot film probes are used, where a thin nickel is deposited on a quartz body, where a special lacquer protects the metal film against corrosion, wear, physical damage, and electrical action. Fiber film probes are especially useful in replicating the Hotwire probes, since the sensor element is cylindrical glass rod with a thin layer of nickel deposited on them. Multiple sensor probes are required for multiple component velocity measurements, the rule of thumb being a sensor for each velocity component. That means you need one sensor for each velocity component. Each probe type is often available with wire or fiber film sensors, whereas single sensor probes require velocity calibration only. Multiple sensor probes require a directional calibration as well as a velocity calibration. Selecting the right probe is very important for the application at hand. The rule of thumb is to use wire probes whenever possible, and as they are relatively inexpensive, have better frequency response and can be repaired. On the other hand, prefer film probes in more hostile environments, as they are more rugged to protect them against mechanical and chemical action. As a trade-off, they have worse frequency response compared to wire probes. In the picture, what you see is a gold-plated 5 micron diameter Hotwire probe, suitable for boundary layer measurements in air. Now let's take a look at the operating principle of a Hotwire. The operating principle of a Hotwire probe is based on heat transfer from a thin, stretched, heated sensor, for example a thin wire, as seen in the picture. When the sensor is placed in a fluid flow, the equilibrium temperature of the wire will typically depend on the heat balance between the resistive heating on the wire and convective cooling. In CTA measurements, the sensor temperature, also the resistance, is kept constant using a dedicated servo amplifier. A change in flow velocity here will register a change in the wire temperature, meaning a change in wire's resistance. The overheat ratio, which is defined by this formula, indirectly defines the operating temperature of the sensor TW. The temperature and therefore the resistance changes can be registered by a Wheatstone bridge, which can be compensated by the servo amplifier by adjusting the voltage to the Hotwire sensor through here. The voltage supplied by the CTA anemometer is indirectly related to the incoming flow velocity. The nonlinear cooling response is established by a velocity calibration where voltage E and flow velocity U follow the King's law. Once the velocity calibration is performed, the measurements are performed by reading the voltage with the A to D converter and converting them into velocities using the calibration information. Once the velocity time series is obtained, standard data analysis routines can be performed. Now let's take a look at the heat transfer relationship at the sensor. The joule heating generated at the sensor is dissipated via conduction to prongs, convection to surroundings, and radiation to the environment. The rest of the energy is stored in the sensor to increase its temperature. For an infinitely long wire, the conduction term can be ignored. Radiation can be ignored unless the measurement is in a rarefied gas. No heat will be stored in equilibrium conditions. Then the Joule heating will be dissipated by convection from the wire. Here the convection heat transfer coefficient is a function of flow velocity and can be written in terms of the Nusselt number, which is defined here. Using the King's law, we can relate Joule heating to flow velocity and temperature difference. The Joule heating can be rewritten in terms of voltage across the wire, which is E wire here. And of course, if you remember in the beginning, we made many assumptions. One of them was about infinitely long wire, which is not the case in practice. For finite sensors, we can actually replace this 0.5 power with the power to the n and find the constants a, b, and n through calibration. In practice, it's also convenient to work with the bridge top voltage instead of the voltage across the wire. So instead of EW, we can write E squared. This relationship relates the bridge voltage to velocity acting on the sensor and with possible ambient temperature changes. Often the temperature during a calibration is constant and the expression reduces to its compact, well-known form, which is the form used typically during calibrations. Finally, this equation is used during measurements to obtain the velocity from anemometer voltages. An accurate velocity calibration relies on an accurate velocity reference. Even in flow velocities where compressibility effects are important, the Streamline Pro Hotwire calibrator uses the compressible gas flow equations based on the speed of sound and Mach number. The velocity computation depends on the pressure ratio, specific heat ratio, temperature, and gas constants. As an example, we can show the typical calibration results of a Dantec 55P61 crosswire probe at room temperature in a relatively low velocity range. A Streamline Pro automatic calibrator was used. A laptop computer was in control of the calibration operation, running the standalone calibration software, recording voltages through USB A to D converter. Typical calibration constants A, B, and N are displayed together with the fit quality, which is pretty good here. As you can see, new sensors on a new probe have very similar velocity response characteristics. We have just seen the velocity response of Hotwire sensors and the velocity calibration. The Hotwires also have a directional response, which allows us to measure multiple velocity components V and W. Measurement of V and W require additional sensors, additional equations, and a directional calibration. In other words, each additional component requires a new sensor positioned perpendicular to the existing ones and a form of directional response equation. In order to formulate the general directional response, we should consider a more general case of any flow velocity UVW in probe coordinates XYZ, which can be decomposed as normal, tangential, and binormal velocity components UN, UT, UB in wire coordinates. The cooling of the sensor is effectively a combination of UN, UT, and UB and is given by the Jorgensen's formula for the effective cooling velocity. Here, K and H are called the yaw and pitch factors respectively. Finally, the effective cooling velocity is coupled to the velocity calibration using this equation: E squared is equal to A plus B U e to the n, where you will realize that U is replaced by UE, effective cooling velocity. Typical directional response of a single normal Hotwire probe at a given velocity looks like a saddle. So when the probe is rotated around the sensor axis here, the effective cooling velocity actually increases, so you should be looking at the theta axis. Whereas when the probe is yawed around the binormal axis, when you yaw the probe around this rotation axis, the effective cooling velocity decreases, so it goes along the alpha axis. The directional calibration factors, K and H, in fact also depend on calibration velocity. It's a weak function of velocity, but often they are taken as constants. As an example, we can show the directional calibration results of a Dantec 55P61 cross-wire probe at room temperature in a ±40° yaw angle range. In addition to the velocity calibration setup, an automatic directional calibrator is used, and the curves for sensor 1 and sensor 2 represent the left and right hands of the saddle point in the directional response, which means that the brown curve here for this sensor is the right hand side of this saddle, and the green curve would be on the other side of the saddle point. Typical yaw constants K and the actual wire angle are computed together with the fit quality. As you can see, once again, new sensors on a new probe have very symmetric directional response characteristics. As a second example, we can show the directional calibration results of a Dantec 55P95 triple wire probe at room temperature in a full 360° roll rotation range. Often a small yaw angle is introduced to break the rotational symmetry of the wires. Once again, the previous velocity calibration setup with an automatic directional calibrator is used. Here, typical yaw and pitch constants, K and H, is calculated. The actual wire angle is calculated, and the fit quality is displayed. As you can see, the directional response of each sensor is shifted 120 degrees due to the symmetric sensor placement around the probe axis. We have now covered the velocity and directional response of Hotwire sensors, and now let's take a look at the dynamic response. The dynamic response of a Hotwire anemometer is a measure of how fast the measurement system can respond to sudden velocity fluctuations. Dynamic response is governed by the response equations for the bridge, the sensor element, and the amplifier. In other words, you may choose a fast responding wire sensor, but if you have a slow bridge or amplifier, you will end up with a slow responding system. The frequency response of a CT anemometer with two-parameter optimization can be modeled by a third-order system. And there are two methods to measure the dynamic response. Either a perturbation is added in the flow, such as a shock wave or an oscillatory flow, or an electronic disturbance is added in the circuit, such as a sine wave or square wave. Of course, electronic testing is preferred, and square wave test is commonly used for the two-parameter optimization. The square wave response of a hot wire and hot film probe is quite different, and hot film sensors are slower compared to hot wire sensors. This is mainly due to the large heat retention in the fiber film substrate. On the top here you see the square wave response of a hot wire, and in the bottom you see the same for a hot film probe. The slower response of hot film sensors can be seen using a sine wave test also. Here you see a sine wave test comparison of a 4 micron hot wire sensor on the left and a 50 micron hot film sensor on the right. It shows that the hot wire probes will have a faster response under the same conditions for a larger frequency range. In other words, the cutoff frequency of a hot wire is 90 kHz here on the left, and the cutoff frequency of a hot film probe will be about 75 kHz on the right. Let's look at the uncertainty sources. Anything that changes the heat transfer relationship other than the fluid velocity is considered an uncertainty source for the CTA technique. These can be categorized as systematic and unsystematic sources. Ambient temperature variations, solid wall proximity, and sensor-induced vortices are some systematic error sources. And sensor contamination, air bubbles in water, probe vibrations are some unsystematic error sources. Ambient fluid temperature is the most critical source and can affect many fluid properties, like the terms marked in red in the equation, such as thermal conductivity, density, and viscosity. The correct form of King's law should then be used, which is the long form, during velocity calibration for temperature correction. As you can see here, different velocity response curves are obtained at different ambient temperatures. To improve the accuracy due to the ambient temperature variations, either the longer form of King's law is used during calibration and measurements, which is this one here, or a correction is performed on the acquired voltage while the short form is used. The correction formula with the exponent 0.55 works well for measurements up to 500 kelvins within 5% accuracy using a cold calibration at room temperatures. In certain passenger comfort applications, ambient temperature variations are not just a correction parameter, but measurement parameter. In such applications, flow velocities are also quite low and often requires temperature compensated circuit design. The ComfortSense systems are used in passenger comfort investigations in aircraft, buildings, and cars. Recently, especially due to the COVID pandemic, these systems are being used in public health investigations, in studies where disease transmission prevention is studied in closed environments. The draft velocity, ambient temperature, operative temperature, and humidity can be measured according to international standards. The probes have research versions for laboratory testing and a mannequin versions for passenger comfort testing. Up to now, we have seen the working principles of CTA, the velocity, directional, and dynamic response of Hotwire sensors, typical error sources, and corrections. We will now look at a typical application of Hotwire measurement in a boundary layer flow investigation. Boundary layers can be laminar, turbulent, and transitional, and the transition location is very important during the design of aircraft, wind turbine, or turbomachinery. The heat transfer coefficients are also different for laminar and turbulent boundary layers. Therefore, the transition location becomes important in the design of heat exchangers or heating and cooling systems. For example, wind turbine blade performance depends a lot on the type of boundary layer over the blade. The nominal blade performance are achieved for new and clean blades, and energy production rates decrease in time due to aging of the turbine blade. Aging typically accelerates due to extreme forces of the nature, such as biofouling or dusty winds, as you can see here on the right hand side. Wind turbine manufacturers often are in search of magic paint or coating material that will stop or at least reduce the aging process on the turbine blade to keep close values to the nominal performance. Recently, we have participated in an EU project called Natural, where the aim was to test different industrial nanomaterial-based coatings. Our aim was to investigate the effects of aging on different coating materials in terms of boundary layer stability. Several plates with different coating materials were abraded and biofouled, the boundary layer characteristics of which were compared to the pristine smooth plate. The experiments were performed at the Yellow Wind Tunnel of DTU, Danish Technical University. The test section was first fitted with a special 3-axis traversing system, which is seen here. It was to perform automated boundary layer measurements over a flat plate. The probe support accessed inside the test section through this sliding window here. And measurements were taken in cross sections at various distances from the leading edge. The leading edge of the plate can be seen here. Across each cross section was approximately 100 millimeters by 10 millimeter, and each experiment took about 3-4 hours to complete. Inside the test section, 2 hot wire probes were used, boundary layer type close to the flat plate and the free stream type, which is out here. The Hotwire probes were operated using 2-channel Streamline Pro anemometer, and calibrations were performed using the Streamline Pro calibrator. Velocity data was collected simultaneously in order to perform normalization between the hot wires using the free stream velocity of 30 meters per second. During the experiments, both probes are positioned outside the boundary layer, while the boundary layer probe goes in and out of the boundary layer. The free stream probe always remains outside. The flat plate was polished to a near mirror finish in order to achieve extremely low roughness conditions. As expected, smooth and pristine flat plate produced a laminar boundary layer in these experimental conditions with almost no turbulent fluctuations, as you can see here. The plot on the left shows the normalized ISO velocity lines every 3 meters per second measured by the Hotwire anemometer, and the colors here indicate the turbulent fluctuations. The picture on the right is from a typical laminar flow visualization study using smoke, which shows a laminar condition. On another plate with a different coating, transitional flow was observed on the smooth polished surface. This was because of the presence of an isolated roughness element. The initially laminar boundary layer is contaminated by some turbulent fluctuations starting here on the right hand side and creeping inside the boundary layer. The flow is transitional on the right hand side, and the effect is spreading leftwards into the boundary layer. This is a typical situation observed at the beginning of a turbulent spot, which can be visualized here in the red rectangle here. On a third plate that has gone through accelerated biofouling, again a transitional flow was observed on the edge surface due to presence of distributed surface roughness this time. This was in the form of organic matter accumulated on the plate. The boundary layer is partly transitional and partly laminar at first, but this time the turbulent fluctuations were observed on the left hand side of the plate and spreading towards the right with increasing distance. This is a typical situation observed on the edge of turbulent spot, which can be visualized here in this red rectangle here. I would like to conclude this session by summarizing the advantages and limitations of Hotwire anemometry. The first advantage is perhaps the cost, which is much lower than the laser-based systems like laser Doppler anemometry and particle image velocimetry. The second advantage is very high frequency response and spatial resolutions can be achieved. Today, commercial wire sensors are available down to 1 micrometer diameter, and some nanometer-sized sensors are being reported in the literature, especially useful in boundary layer applications. These sensors, driven by well-designed electronics, can achieve megahertz level frequency response. A third advantage is the accuracy, where 1% accuracy is quite typical, and 1 probe mil is achievable with experienced users. A signal-to-noise ratio of 10,000 is quite standard with research-grade CTA systems. On top of this, the technique is simple to operate and does not require seeding, which can be quite problematic actually in large open return wind tunnel facilities. The signal analysis is quite straightforward and spatial correlations can be performed. And finally, the hardware is quite compact and therefore can be used in mobile applications such as flight testing. There's also some limitations. The list of limitations start with the calibration. An accurate CTA measurement requires an accurate velocity and directional calibration. CTA is a point measurement technique and requires traversing to perform profile, area, or volume measurements. Furthermore, it is an intrusive technique as it requires the placement of the Hotwire probe in the flow field. These two last limitations, the traversing and the intrusive measurement, often require custom designed traversing systems for each experiment. As mentioned earlier, there's a number of error sources such as ambient temperature, fluid density, viscosity, thermal conductivity, etc., which can be corrected with careful post-processing of the signal. Because the cooling of the sensor can take place from any arbitrary direction, the hot wires are actually unable to identify flow direction. So the experimental needs to have a general idea about the flow conditions. The final limitation is that the wire sensors are quite fragile as they are quite small. Therefore, using wire sensors in particulate flows can be quite problematic. In such instances, hot film sensors should be preferred. As concluding remarks, in this seminar, our aim was to provide a basic theoretical introduction to CTA, and I will try to answer your questions here now. However, before we start to take some questions, I would like to recommend a textbook by Brun, Hotwire Anemometry, Principles and Signal Analysis, and a chapter edited by Goldstein in the book Fluid Mechanics Measurements. If you need more in-depth formulations about hotwire measurements, you can refer to these texts. Finally, I would like to remind you to stay tuned for upcoming webinars, and thank you very much for your attention. I can take some questions now.